Okay, thanks a lot for the nice introduction. And it's really great to know that you are using our VTech dataset. That's a great pleasure. And I'm very honored to be here today to talk about our recent work on tackling data scarcity in vision and language. Okay, so in the past few years, we have witnessed a great progress in the emerging area of vision and language. Back a few years ago, like when people are working on visual question answering, we typically use the simple CNN model plus some LSTM layers to perform the task, and now so there are a lot of advances in this area. Like from the visual side, we are going from passive perceptron to active perceptron. Like previously, we may only work on static images, but now we can even even empower embodied agents to be inside a 3D environment and produce certain actions to interact with the environment. And also for many tasks, we are going from static imagery to real world environments. And from the language side, we go from templated language to more and more natural language in some practical environments. And so, for example, and also we go from single turn language interaction to multi-turn language interaction. Like previously, we may only ask a question and expect the model to answer the question given an image. And right now, we can even talk about, we can even freely talk about with a machine learning model about the content of an image or a video. And more recently, so the community is working more and more on multitask generic representation learning for those language and vision tasks instead of task-specific in domain learning. And for example, like those real-world models, and you may also heard of the DALE model. It's a very impressive model, like to generate some novel concept, even some compositional novel concept given a natural language query. And yeah, as we know, deep learning has obtained great progress in vision in many fields, including vision and language navigation. But what enables deep learning? First, algorithm. For example, convolutional neural network, recurrent neural network, and transformers, deep reinforcement learnings. There are numerous advanced deep learning techniques, and this is also what we would like to believe, some elegant algorithms that can work perfectly. But meanwhile, we cannot deny the significant contribution of the computational power and this access to large-scale data. And in my opinion, data is really the key here. The CNN is out there for many years, but only till recently CNN has been deployed into many areas successfully. That's because of the development of the computing power and access to more and more large-scale data. So data is really key here. But data scarcity is also a big problem. And first, deep learning requires big data, which is often prohibitively expensive to collect. And deep reinforcement learning is impressive but brittle, which suffers from high sample complexity. And in general, those models break under distribution shift. In other words, so they could achieve amazing performance on some same training data or same environments, but perform poorly on outer domain data. Let's take an example of natural language grounded navigation. Here we show this example, okay, sorry. Here is an example of natural language grounded navigation, where we can place a robot inside a 3D environment and then ask the robot to do something like, can you grab me the plant? The robot may ask for a clarification question, like, sure, where is it? Then we, as a human, we may provide further instruction like get out of the room and go towards the kitchen, and the plant is on the window near the kitchen. And as you can see, it requires the understanding of the natural language communication and the visual perception, as well as the alignment of those two modalities, right? And for such kind of tasks, so to collect the human instruction is really hard. First, you have to have a person to perform inside some interactive environments, and then ask the person to label the instructions for you. And so compared to other tasks like image recognition or object detection, where you only simply need to label an object inside the image, although it is also hard to collect, but I think for challenging vision and language tasks, including natural language grounded navigation, it is much harder. First, those real world experiments are not scalable, and second, if you are going to work with simulation environments by reconstructing from the 3D room scans, then the 3D room scan and the reconstruction itself is limited and expensive. And as I said before, human instructions are hard to collect in interactive environments. And so it suffers from poor generalization issue. Models tend to overfit those same environments and perform poorly on unseen environments. And this poor generalization issue is actually applied to many other domains. And in this talk, I'm going to mainly discuss and talk about our recent efforts on tackling data scarcity in such challenging vision and language tasks, including VLN, vision and language navigation, and other tasks like language-based image editing. And we will mainly tackle the issue from 3 perspectives: self-supervised counterfactual reasoning, multimodal style transfer, and multitask learning. Okay, counterfactual thinking is a concept in psychology that involves the human tendency to create possible alternatives to life events that have already occurred. And here we combine the power of self-supervised learning and counterfactual reasoning and apply self-supervised counterfactual reasoning to multiple tasks. So first, I'm going to talk about our recent work, NLP paper on proposing the self-supervised counterfactual reasoning for the task of iterative language-based image editing. So here is the task. So basically, we all know what is the task of image generation, right? So for image generation, you could also think of the task of conditional image generation. So let's say, giving a language description, you can generate an image that matches the given language description. And here we we are interested in even more challenging task, iterative language-based image editing. It's like, so because intuitively, when we generate an image using a model by communicating with it, then it is always not done by one turn, and we can always provide some further clarification to generate the desired image we are looking for. So, for example, in this case, at the very beginning, we can see, you know, can you add a blue cylinder at the center, and then the model may receive the instruction and do the job for us, and then we can iteratively provide further instructions like add a purple cube in front of it on the right, and then add a red cylinder in front of it on the left and in front of the blue cylinder on the left. And to accomplish this task, models are required, you know, not only to modify images, but also to understand the visual difference between the previous and resulting image based on the given instructions, right? And here is another example of this task where, you know, for example, this task is collected by how two humans interacting with each other. Like one is the teller to tell the other to draw an image, and the other is a drawer which communicate with the teller and draw the image as the teller wish. So here is a baseline model for this task, which is a conditional GAN, which consists of two components, a generator and a discriminator. So the generator basically is conditioned on previous images and the recurrent instructions, like giving the previous image and the instruction history, the generator is supposed to generate the resulting image. While the discriminator here is also a conditional model, which conditions on the recurrent instructions. It is supposed, you know, to tell whether this image is generated by a human or not. And here, as you can see, if we test the model, this baseline model, using different percentage of the training data, it actually suffers from data scarcity a lot. Like if we are using, we are only using half of the training data, you see there is almost more than 10% drop on the performance. And as a human, we can actually imagine some counterfactual situations, even though lacking some previous experience with those images and instructions. So although we as a human are not trained to draw such images given the instructions, but we can still imagine what it would look like if, you know, if given a counterfactual instruction. See, for example, here, maybe, you know, the previous instruction can be given this input image, the ground truth instruction can be, you know, add a red sphere behind it on the right. And as human, we can think how the resulting image would look like if given a counterfactual instruction like add a sign Infere in front of it on the left. And this is actually an out of distribution instruction that doesn't exist in the training set. So in order to combat the data scarcity issue, so the first solution here is to do instruction intervention. So where we consider those counterfactual outer distribution instructions. And to do that, we basically replace some tokens with randomly sampled tokens of the same type. For example, given those two data sets, iCLEVR and CoDraw, we first define some token types like color object relation in iCLEVR and size object relation in CoDraw. And then given a random training instruction, we can replace a certain type of token in this instruction with some other randomly sampled tokens of the same type. For example, here we can replace the color token red with sign, the relation token behind with in front of, and the direction token also, or the relation token right with left. But the question is, for the original instruction, we do have the resulting image, the ground truth image, as they were already collected by some human annotators. But for this counterfactual instruction, we don't have such kind of supervision. Then it remains a question how we should obtain the supervision for counterfactual instructions. So the solution to that is the cross-task consistency we propose, where we introduce in addition to the conditional GAN model, the interactive editor to generate the image given an instruction and the previous history, we introduce an iterative explainer to explain the editing history with instructions. You can view it as a back translation model. Given the previous history, we can actually generate some instructions to describe the editing history. And this provides token level auxiliary loss by comparing the original instruction and the reconstructed instruction. And this is how our model would look like, and iterative editor with the cross-task consistency. And previously, given the image and instruction history, we use a generator to generate a new image, and then we use a discriminator to provide the supervision towards realistic image generation. And now additionally, we provide a cross-task consistency as an auxiliary supervision to validate, if the reconstructed instruction is aligned with the original instruction. And finally, our self-supervised counterfactual reasoning would be a combination of the counterfactual instruction and the CTC, the cross-task consistency, as self-supervision. And now let's consider some counterfactual scenario here. So now, given an image from the data set, we can actually create a counterfactual instruction here, which is not associated with any ground truth resulting image, right? And then we can still employ the generator to generate an image. And then we can use the cross-task consistency to reconstruct an instruction from from the resulting image and the editing history. And then by comparing the reconstructed instruction with the original instruction or the counterfactual instruction, we can actually know whether the resulting image matches the counterfactual instruction or not. And then we use this kind of self-supervision to train the model for counterfactual reasoning.
I have a small question about this, if I can.
Mm-hmm.
So, do you think so? If can you train this network without supervision? So, what I'm trying to say is, can you? So, let's say that you don't have the ground truth images at the end, but can you use cross-task consistency to train this network? Only
Yes.
cross-task consistency.
Okay, so if you mean only cross-task consistency to train the network, to train the model on the whole data set? Is
Yeah.
that what
Like
you mean?
how good would it be compared to
Oh,
your model?
okay, so that is a error that would be an error accumulation issue. So it actually it doesn't work quite well because of the error accumulation. As this cross-task consistency model is also pre-trained on the dataset,
Oh, I
and
see.
if there is not some regularization from the ground truth signal, and then it would not work really well.
Yeah, that makes sense. Okay,
Mhm.
thanks.
And here are the results on two popular benchmarks for this task, iCLEVR and CoDraw datasets. So to evaluate the image generation, basically we are employing two kinds of evaluation metrics, precision recall and F1, which basically match objects between the prediction images and the ground truth images. And the other is real sim, which considers both the object matchness and the related position accuracy. And GeNeVA is the baseline method we just introduced. And if we are going to use the CTC only, here CTC only means, we use the CTC, cross-task consistency, as an auxiliary loss in addition to the GAN loss without counterfactual reasoning. So basically, we train the model on the full training set and test it on the test set. We don't augment any counterfactual instructions. So if we are going to use the CTC auxiliary loss only, then we also, it is also noticeable that we can achieve some improvement. But if we are going to augment the training set using the self-supervised counterfactual reasoning, then it can achieve an even larger performance boost. And here are some results under data scarcity. X-axis here is the percentage of the training data set we have used. And y-axis is the evaluation metrics, including F1 and real sim. And as you can see here, so the blue line is the baseline model, and the orange line is it's our model with the CTC loss, and the green line is the self-supervised counterfactual reasoning method, the final model we are using. First, as you can see, the Caesar model, a self-supervised counterfactual reasoning, is more robust under data scarcity. And it can even achieve similar performance with the baseline model with full data, even when using only half of the data. Like for example, if you look at this figure, you see the Caesar model with only half training data can even achieve similar performance with a baseline model with a full data. And here I would like to show a visualization of the generation process, or case study. So first, the instruction would be like, on the left side is assign media size. Then you see compare with the baseline model. The Caesar method is actually generating some more reasonable image. And then giving another instruction below the sun is a girl facing left with her left hands up. So the Caesar method is clearly better than the baseline model, but you may notice that for this image, this girl doesn't actually raise her hand. So I would say it's still a very, very challenging task. And though our method can mitigate the data scarcity issue, but there is a still long way to go for this task. And another instruction, the girl is small on the far right is a boy. And another one down corner right is a very small cat facing left. The baseline model totally missed the point, but so it may not be very clear, but the Caesar model actually generated a cat behind the boy here. Okay. And another one is a big tree almost in the middle with a hole in it, looks a bit right. And in the middle of the sun, it's an orange toy almost on horizon. Okay, so as you can see, this Caesar method is actually working quite well on the interactive image-based, language-based image editing task. And we also test the counterfactual reasoning on the task of vision and language navigation. And before talking about the method, I would like to further introduce the task of vision language navigation, where the agent is supposed to navigate inside a 3D environment by following a natural language instruction without the access to maps or GPS. And it produced actions like turn left, turn right, look up, look down, go forward, and stop. And in the end, the agent must stop at the target location to fulfill the task. And note that at each location, the agent is receiving first-person egocentric view as we do, as humans do. Okay, so to basically to employ counterfactual reasoning for the task of vision and language navigation, because the data collection for VLN is also prohibitively hard to collect. So for this data set, you may know that for MS COCO data set, there might be millions of images that you can use. But for the task of VLN or the image editing task, there is only like 10,000 samples to use. But we can actually incorporate counterfactual reasoning to augment some data for us. So think about that. If we, in addition to following, the exact instructions given in the training set, we can actually do some counterfactual reasoning here. Like what if we stop in front of the dining table instead of walking away from it, what should be the instruction be? Here we basically do the counterfactual reasoning on the action taking process. So to do that, we introduce adversarial path sampling methods to take counterfactual actions and sample increasingly challenging paths. And then we can employ a speaker model, a back-translated speaker model, to augment those paths with new instructions. And hence, we can train a more effective VLN agent based on the combination of the augmented data set and the original training set. And here is how data augmentation with the speaker model would look like. So the training set only covers limited paths instruction pairs, and we can actually randomly sample paths from the training environments, and then use a speaker to synthesize instructions on paths to form an augmented data set. So given a training environment, we can randomly sample a path from it. And then the speaker, which is pre-trained on the training set, can generate an instruction for this sampled path to form an augmented data. And then we can train the agent on the union of the original training set and the augmented training set. However, from our observation, those randomly sampled paths are very inefficient. So look at this figure here. X-axis basically represents, how much of the augmented data we are going to use. So 0% means we only use the original training set without any augmented data, and 100% means we are using 100% of the augmented data set. And you may notice that the y-axis is the success rate, which is one of the primary evaluation metrics for the task of VLN. You may notice that here basically we can see using the augmented data set improves the performance, right? However, the success rate does not increase as more augmented data is used. And basically the performance stop improving at nearly 60%. So we argue that randomly sampled paths are inefficient because they are too arbitrary. And therefore, we propose an adversarial path sampling method to sample increasingly challenging paths, which the navigator cannot navigate easily. So it's a adversarial process here. Basically, we have a navigator which is trying to accomplish those augmented paths from the APS, the adversarial path sampler, and therefore optimize for a better navigation policy. And meanwhile, our APS will sample increasingly challenging path for the navigator to accomplish. And here is the comparison between adversarial path sampling versus random sampling. As you can see, APS is much more effective and efficient. First, the performance gain from APS is certainly larger than random sampling. Second, it keeps improving as the augmented data increases. And APS, the APS approach is also model agnostic. We basically apply the method of APS on 3 baseline models: the sequence-to-sequence model, the speaker-follow model, and the RCM model. And as you can see, APS consistently outperforms random sampling on all those three models. Here we basically present a smart method for data augmentation, which can be applied to all kinds of VLN models. And we also believe that this adversarial data augmentation method is generic and can be applied to other domains. And okay, so in this paper, we also modify the pre-exploration approach proposed in the other works. So we argue that environment-based pre-exploration is more practical. Okay, but for the time concern, I will just skip this. If you are interested, just look at the paper. And here is the results. Here is also the results on pre-exploration. Basically, APS method helps on both sane and unseen environment, and the pre-exploration with APS further improved navigation on unseen environments. Okay, so here are some takeaways for counterfactual reasoning. First, counterfactual reasoning is an essential ability for model generalization, which basically enriches data augmentation approaches. And self-supervised counterfactual reasoning demonstrates its effectiveness and robustness on both generative and navigation tasks. And last but not least, self-supervised counterfactual reasoning is a general method and can be applied to other tasks. Okay,
I have a quick question.
Mm-hmm.
So other areas have observed that there's like a accuracy and robustness trade-off, right? With adversarial training, your accuracy on the in-domain data set will fall, but it doesn't seem like you're observing that here. Is that because of the language modality, counterfactual being, language-based, or can you comment on that?
So, good question. So basically, you are saying that the worst, you are saying that adversarial training usually suffer from the robustness when applied to data of the other domains. Is that what you are saying?
I'm just saying in other areas like classification, specifically image classification, it's been observed that there is a trade-off between in-domain accuracy and robustness achieved via adversarial training. And it doesn't seem like you're observing that in your experiments. In your experiments, just as you showed, it's the adversarial training actually improves generalization and probably in-domain accuracy as well. So I was just wondering if you could comment on why you think that trade-off doesn't exist within this specific experiment.
That's a very good question. So a big contribution of this work is that we are using adversarial learning, but it's not a Euro-GAN model, as you can see. We are using adversarial learning to augment the data rather than to push the accuracy on the original data set. So the key difference here is that we actually augment some other domain data for the task, so that it would not suffer from the issue you are mentioning.
Yeah, it's a bit hard to visualize, but yeah, that makes sense. Like it's just a different formulation, counterfactual versus minimum accuracy of the model in some perturbation, right? Yeah, so makes sense.
Okay, next I'm going to introduce the other approach we propose to tackle the data scarcity issue, which is multimodal text style transfer for outdoor vision and language navigation tasks. So previously we introduced the speaker model, and in both, basically in both papers we mentioned before, we basically employ the idea of speaker to augment the data, right? Like we use a recurrent speaker or iterative explainer to generate sequential instructions given the resulting image. And we then, for the VLN task, we use a speaker to generate the instructions given the sampled path. But there are some certain limitations of the speaker model. First, it is pre-trained as a vision and to language generation model and expected to generate those instructions from scratch, right? So let's say for the VLN task, given a path, then the speaker model is supposed to generate the instruction purely from the visual path. And this would be particularly challenging in more complicated environments than indoor environments. For example, the outdoor vision and language navigation task on the street view is a much more challenging task where there is more complicated and diverse visual perception, and the navigation paths are usually longer. And from the instruction perspective, the instructions are often more linguistically complex. And again, there is limited number of human annotations. It's very expensive and time consuming to collect those kind of human instructions. But in order to overcome the data scarcity issue, we can actually leverage some external resources like Google Street View to help outdoor navigation. So basically for Google Street View, so we are all using Google Map probably. Then basically we can use the Google Map API to produce some template-based instruction to provide some learning signals. But the challenge is that those Google Map API instruction, their styles are quite different from human descriptions. For Google Map API instruction is typically refers to the exact names of the streets, and then plus some directional signals like turn left, turn right. But as a human, when we are directing someone on the street, we usually refer to the surrounding environments on the street. Like we often refer to the buildings, the shops, and some other objectives, and some other objects on the street. So to effectively utilize those external resources like the Google Street View and those templated instructions, we can actually work on creating pre-training data sets for the task of VLN. Like here, we can basically, theoretically, we can sample any path on Earth using the Google Map API. And then if we can figure out how to transfer the style of the Google Map API instruction into the human instruction style, then basically we can access to a huge amount of external resources for the task of VLN, right? But one idea, is to use the speaker model to, to do the back translation from given the visual path. Yes, we utilize a speaker model to generate the instruction from scratch. But this is hard, particularly hard outdoors because of the additional challenges of the outdoor environments. Here we show an example. We can see, the instruction generated by the speaker model is actually in poor quality, in the sense that the directions and objects are not aligned to the real path and therefore misleading. So to better utilize the external resource and overcome data scarcity, we propose a multimodal text style transfer learning approach for the outdoor VLN task. And this framework mainly consists of two modules: a multimodal text style transfer model and a VLN transformer, which is a navigation model. The multimodal text style transfer model is used to transfer, the API, Google Map API generated instructions into the human written style, which is to narrow the gap between the human annotated instructions for the VLN task and the API generated instructions in the external resource. And note that it is trained on the outdoor VLN dataset. And I will introduce the training and the inference of the multimodal text style transform model later. And next, when we train the multimodal text style transform model, or MTST model, we can apply a two-stage training pipeline to train the navigation model. Basically, we use the MTST model to construct a pre-training data set for the VLN task, and then we can pre-train the VLN transformer on the external resource, and then fine-tune it on the outdoor VLN dataset. And the objective, is to transfer the API style instructions into human style instructions while keeping the guiding signals provided by the Google Map API. And the main difference between, as we said before, the main difference between human written instructions and those API generated instructions is that humans often use the surrounding objects to refer for reference and guidance, while those API generated instructions emphasize more on those exact street names. So in order to transfer the instruction style, we need to inject those objects information into the API generated instruction. And to do this, we propose a masking and recovery scheme to train the multimodal text style transfer model. So during training, we mask out the object tokens in the instruction. And then the MTST model basically, takes both the trajectory and the mask instruction as the input, and then try to recover the missing objects given the visual path. And the learning signal object here is basically, to classify the correct object tokens in the mask instructions. And after training, we use the model to transfer the style of API generated instructions. So for inference, we mask out the street names in the instruction. So now, this is an instruction from the Google Map API. Then we mask out the objects in this instruction. And then we employ the MTST model to fill out the missing objects. And as a result, the generated instruction will have similar style as the human written instructions, as now it refers to the surrounding objects instead of the exact street names. And we compare the instructions, generated by the MTST model and the speaker model on 5 commonly used benchmarks, commonly used metrics for language generation, like Blue, Meteor, Root, Cider, and Spice. And obviously, the transferred instruction quality is much higher than speaker-generated instruction in terms of those automatic metrics. And actually, we also compared, the diversity and the occurrence of the object tokens in the generated instruction. And the MTST generated instructions have much richer object tokens than the speaker generated instructions. Okay, we can look at the case we showed earlier. You see the speaker model have a poor performance in keeping the correct guiding signals, and it also suffers from hallucination, which is referring to objects that have not appeared in the trajectory. Like it says, a red brick building with a red awning, which doesn't actually appear in the visual scene. In contrast, the instructions generated by our approach is more aligned to the trajectory. And it also successfully injects object information to the instruction, even though this object never appeared in the ground truth instruction. And in addition, we also introduced a new navigation model, VLN transformer, which it's the first transformer-based model for the outdoor VLN task. So basically, we use the broad-based instruction. We use a broad-based instruction encoder to generate embeddings for each sentence in the instruction, and then we use a CNN-based view encoder to obtain visual features for the visual views at each time step. And then we use a cross-modal transformer to fuse the features together from different modalities and jointly encode the instructions and the trajectory. And finally, we concat the output together and then feed them into a fully connected layer to predict the action for the current step. And we conduct experiments on the touchdown dataset for the outdoor VLN dataset, for the outdoor VLN task. And this is the target outdoor VLN dataset. As for the external resource, we use the street-learn dataset. So basically, for the touchdown dataset, both the trajectory source for touchdown and street-learn are from Google Street Views. While for the touchdown dataset, those instructions are annotated by human annotators, while for the street-learn, the instructions are basically from the Google Map API. And then we use our MTST solution. We use our multimodal text style transfer to create a stylized augmented dataset M50 by transferring, the instruction styles of the street-learn dataset. And here we show the outdoor navigation results on the touchdown dataset. First we compare the VLN transformer with the baseline concat model. And then, so our VLN transformer those are consistently outperforming the baseline model. And then we also compare the performance on the M50 dataset, which basically we pre-train the model on a street-learned subset with API-generated instructions. In other words, on the augmented visual paths without doing style transfer. And M50 plus style means that we pre-train the model on the augmented visual path with the stylized instructions. And as you can see, basically it shows that pre-training on external resources is helpful for improving the task completion rate. But note that stylized instruction bring the most significant improvement, which basically validate the effectiveness of the proposed multimodal style transfer approach. And we can also see that pre-train the model with stylized augmented data improve the navigation performance for both ArchonCat model and the VLN transformer. So yes, this approach is again model agnostic and generic. You basically can apply it into some other navigation models. So here are some takeaways. First, do not limit yourself to existing label dataset, because the label dataset is only a tiny bit of the entire world. So for example, so every day there are like billions of videos uploaded to the YouTube. But so for example, vtext is a great dataset. The instruction quality is good because we control the quality with a very strict criteria. But vtext dataset is still, although it's large scale, but still a tiny bit of the entire video dataset. So you may think of using some available YouTube videos as some external resource and then outperform all the methods on the vtext dataset. And second, pre-training can help, but be aware of the distribution shift between the pre-training and fine-tuning data. So sometimes it might not that trivial to directly train a model, pre-train a model on some external resources. And multimodal style transfer enables effective utilization of all available data on Google Maps, potentially. And last, I will talk about multitask learning. How many minutes do we have? How many minutes do we have left?
I think we have like 15 minutes, roughly.
50 minutes or 15 minutes?
15, yeah.
15 minutes.
Right. Dr. Yang, you might have muted yourself.
Oh, Eric, we would also appreciate to have a few more minutes for discussion and Q&A at the end of the session.
Okay.
So
Okay.
Let's say 5 more minutes. Will that be enough?
Yeah.
We can always encourage the audience to refer back to your papers as well.
Yeah. Of course. I can finish this part more quickly.
Thank you.
Okay. So multitask learning is a natural way for data augmentation because you can utilize those label data sets for different tasks and try to transfer the knowledge across tasks. And so here we introduce, for this work, we basically introduce an environment-agnostic multitask learning for generalized navigation tasks. And this is the VLN task. And we also considered another challenging task, cooperative vision and dialogue navigation. So for VLN task, basically, given an instruction in the beginning, the agent is supposed to receive the instruction and then produce some actions to reach a destination. And then the job is done. But here for the CVDN task, basically there are two agents. Navigator and Oracle. Both are given a hint. And then the navigator is supposed, to go towards the goal room, and it can stop anytime, but it can also stop anytime to ask a question for clarification. Let's see, it may ask, so I'm lost. Can you help me? Which direction should I go next? And then the Oracle basically forces the next best steps and answer the questions. And there is subtask. So given the dialogue history, to predict the navigation actions that brings the agent closer to the goal room. So this subtask is quite close to the VLN task. And here we are doing multitask learning for VLN and the task of navigation from dialogue history. So basically we build upon a strong baseline for VLN, the iCLEVR model, and then we propose a multitask iCLEVR model where it's very simple. So we didn't change the model architecture at all. Instead, we basically adopt interleaved multitask data sampling strategy. So we basically modify the data sampling strategy and the reward functions for both tasks. And so we introduce a multitask reinforcement learning, and which would have different reward functions for the task of VLN and the task of NDH. And basically, from our results, we show, the NDH task benefits from VLN consistently, and VLN task benefits from NDH with more fine-grained information about the paths. And if for this task, extending visual paths alone is not helpful. And multitask learning improves the generalization of the task. The performance gap between sane and unseen environment is reduced. Like the performance gap between in-domain and out-domain data is reduced. And we also do some ablation multitask learning. And in addition, we propose environment-agnostic representation learning to learn some invariant representations that is agnostic to certain environments. And I think you can refer to the paper for more details about the approach. And we compare the environment-agnostic approach with the environment-aware approach. So the environment-agnostic approach performs better on the unseen environment, while the environment-aware approach performs better on the same environments. And here are some takeaways. Environment-agnostic learning helps generalization by learning invariant visual representations, and multitask learning transfers knowledge across tasks. And yeah, data scarcity hasn't been solved yet. That's that's for sure. So that those are only some initial steps towards tackling data scarcity. And in the future, we may work on general multimodal representation learning. And right now, we are actually working on general video and language representation. We are working on building a leaderboard for general video and language representation learning tasks. So where we include different kinds of data sets and tasks like VTEX, like video captioning, video question answering, video text retrieval, and some other data sets like TVR, TVQA. And I think in addition, we also need to have a deeper analysis into vision and language into vision and language task. And by the way, so in addition to pushing the accuracy and the performance, we definitely need to think about the harms the machine learning model can bring. So we recently have a paper and a review on mitigating gender bias of gender neutral queries in image search. Like here, so for example, if you type a gender neutral query in Google search, like a person is playing basketball, you may notice that only 1 out of 5 top returns it's related to women. And the other 4 are all about male. So we formally defined this fairness issue, this gender bias issue, and introduce some techniques to mitigate the gender bias of the gender neutral queries. Thank you so much. Here are the references of the papers I just introduced and the corresponding GitHub pages. Thanks.
Yeah, thanks, Eric. So I think we can take some of the questions. If any audience have any question that would like to discuss with Eric, this is the chance.
Oh, I actually have a couple of questions, Eric. It's a great talk. Thank you again. When you are using the speaker model as well as the text transfer models, one thing that is inevitable is that these models are not perfect, right? So you are also introducing potentially incorrect training samples into the original training set, which the original training set is with high fidelity because that's tracked by human being. So do you observe any, do you have any insight with respect to this? And what's the experimental data showing how significant this impacting your performance?
So yeah, that's a great question. So the speaker model, the back translation model is definitely not perfect. But so first, in those papers, we basically proves that even with some augmented imperfect data, we can actually use them to improve the performance. But we also noticed that if you are going to use the augmented data solely, then it would not work well. And so that basically limit the size of the augmented data. So that is certainly trade-off. You can find some sweet point like between the performance on the test set and the size of the augmented data. So if it is too large, then some noises introduced by the imperfect speaker model may overrun the benefits it can bring. So
I see. So I just want to clarify, when you are doing the testing, do you also augment the testing data?
No, yes or no. So in most of the cases, we only augment the training data, but only for the vision and the language navigation. When we do pre-exploration, we basically use the APLs method to pre-explore the environments.
I see. I see. I see. I'm not that familiar with VLN, so I'm also wondering, for example, a fairly basic question, right? You're following a sequence of instructions to reach a certain location. So what if one instruction is not followed? Do you deem that whole trial as a failure? Or you are also depending at which step the model fails to evaluate them?
Yeah, that's a good question. So there are different kinds of evaluation metrics now. So in the very beginning, we only evaluate by the success rate, which is basically if the agent reached the destination, then we consider it as a success, otherwise a failure. So we didn't care about the trajectory at all, but that's erroneous, right? So that cannot verify if the agent has actually understood the instruction or not. So some other metrics were then introduced, like the CLS metric. Basically, those metrics try to evaluate whether the produced trajectory is aligned with the ground truth trajectory.
I see.
So, and so basically, combining those two metrics, we can somehow have a fair evaluation of the navigation agent.
Thank you. Let's see if we have other questions.
Yeah, actually, I have one question. So Eric have given us a very good suggestion. Actually, back to the his like second adversarial, the path sampling way. The third one, the style transformer VLN model. So will he have utilized a transformer model to first do the style transfer to the API, to the Google API text descriptions, and with that, we can further generate more this the human style textual description that can be utilized for VLN pre-training. And Eric have like suggested we can probably utilize the the more videos from the YouTube, for example, and then we can find a way that can give us a way to leverage more additional visual videos, and then back to the VTEX data side, we can probably yield a better performance. I think that's a very practical suggestion. I think that can be, we definitely want to try that. So one question that I think is more like an opinion than a question is that, so if you take a look of the ImageNet challenge right now, especially when the Google, Facebook, they have proposed so many larger models like the VIT, they have pre-trained this VIT model, transformer model on like 300 million data set, which is never released to the public. But this nowadays people are more utilizing these weak labels and unlabeled, or using the self-supervised vision pre-training method to pre-train on larger models. That somehow, like in my opinion, address the data scarcity problem you have identified. And do you really think that will be the future? Can it like become the main one of the training way for the future? Like in the future, people were just utilizing the mixed data. Probably people are utilizing a very large scale unlabeled data, do the self-supervised training, and then do the fine-tuning on the label data. Do you think that can be a mainstream in the future?
Yeah, I think so. I feel like eventually maybe people only collect data set for evaluation. So all the raw data you can use for training. You can use for learning a machine learning model, and then the collected data set are purely used for evaluation purpose.
Right. That can be a very that can be a lot of things, a lot of works to do. I can imagine, like if that's the future.
But that is a very long way to go towards that. But I do think we are going toward that direction. Like there are a bunch of work on self-supervised learning, semi-supervised learning, and to utilize those external resource. We are seeing more and more such works in the field. Yeah.
Right. All right.
It's not a bad thing to see a long way, which means you can build a whole career approaching a hard problem that may never being solved, right? So it's not not a bad thing. Anyway, thank you, Eric, for joining our seminar. It's really great to have you here today. And let's see if we don't have any other questions. Let's thank the speaker one more time. And hopefully we can see each other in person sometime.
Yeah.
This year, one of the conferences to catch up.
Yeah, definitely. I'm looking forward to some in-person meetup.
Hopefully this iCCV. I'm having a fairly high hope that iCCV will be half in person, half virtual.
I don't know. I don't know. I'm not so sure. Hopefully.
All right. Thank you. Enjoy the rest of the evening. Bye-bye.
Thank you so much for inviting me.
We'll follow up. Bye-bye.
Okay, bye.
Bye-bye.
Thanks.
Thank you all for joining. Bye-bye. See you.